Okay. Hey everyone, happy Thanksgiving. I have the great pleasure of introducing Professor Clary Tomlin as today's speaker. Dr. Clary Tomlin is a professor of electrical engineering and computer sciences at UC Berkeley, where she holds the Charles Dizor Chair in Engineering. Clary received the Bachelor of Applied Science in EE from the University of Waterloo in 1992, Master of Science from Imperial College London in 1993, and the PhD in ECS from Berkeley in 1998. She held the positions of assistant, associate, and full professor at Stanford from 1998 to 2007, and in 2005 joined Berkeley. Clary works in hybrid systems and control and integrates machine learning methods with control theoretic methods in the field of safe learning. She works in air traffic systems, unmanned air vehicle systems, and in systems biology. So please join me in welcoming Professor Clary Tomlin. Clary, the floor is yours.
Thank you very much, Guanya, and thank you for inviting me to give a talk in this seminar series. And thanks for organizing this seminar series. I'm going to talk today about work that we've been doing for really, I would say, the past 2 decades in computing safe controllers for autonomous systems, and in the past decade in computing learning methods to integrate with these safe controllers. If you have questions, please, you can, if you're on the Zoom, you can unmute yourself and ask the question. If you're on YouTube, please just put your questions in the chat and Guanya will ask those questions. There's probably some natural times to ask questions, but you can ask questions at any time. Okay, so I'm going to present today. I know what's happened with, just 1 second. Huh. The computer is not, oh, there we go. All right. Let me just test this here. Yeah, okay, good. All right, so today I'm going to talk about the focus of this seminar series is control meets learning. And as I said, we've been thinking about this for quite a while in the concept of safety-based control systems. And that's something that my group has been working on for a long time, how to compute controllers which move towards making guarantees about safety properties of the system. And this is really important when you have autonomous systems that are working in the real world, in close proximity with people. You want to make sure that they don't crash into people. So here's these vehicles from Skydio. One of my students, Samuel Bansal, who's done some work I'll present in this talk, spent a summer internship, actually longer than a summer internship at Skydio. And also Neuro makes an autonomous delivery vehicle. And a couple of my students have spent time also working at Neuro. So these are systems that are, I mean, they're really exciting, right? They've got onboard cameras. They're using these cameras and other sensors to perceive the world around them and then react and, you know, follow desired trajectory, but also maintain safety. And safety is paramount for these systems. As you can see, they're operating in regions where people are involved. You know, pedestrians, people who are, you know, Skydio makes this vehicle as kind of a flying camera. So you can use it to, you know, track sporting activities, for example. And so, you know, there's lots of potential for coming in close proximity with people. All right, so I'm going to talk about the safety-based control work to set the talk up first, to set the talk up. And then I'm going to talk about how to, or how we have, I would say, made some first steps into integrating machine learning into this reachable set framework. Okay, and I kind of put these 2 notes, computation. So in the first case, it's a, you know, for computing this, for people in control, they know that that if you're doing any kind of optimal control or game theoretic method, computation is a big deal. So that's been a big focus of our group. And as I said before, the big part about the second method is it's data driven. It's the systems are collecting data typically about the world around them in real time, and you'd like to be able to react to those. Okay, so this is the concept of a backwards reachable set. This is the kind of core, one of the core technologies that we've been developing in my group for a while now, which is that of a reachable set. And the idea is, I think, quite intuitive. If you've got a system, I just wrote it as a differential equation here. We've done these computations. Most of the computations we're doing now are for, well, it's still continuous time or discrete time continuous systems, but we've also developed this tool for hybrid systems. So systems where you're switching between continuous dynamics and discrete modes. So there's discrete phases of the system. You've got these discrete switches, but then in each phase, there are continuous dynamics which govern the behavior of the system. But for this slide, let's just think about a control system governed by f of x, u, d. U is a control input, d is a disturbance. And let's suppose we have, within the state space of the system, suppose we could characterize ahead of time, for now, what it means for the system to be unsafe. And here I've represented, and then furthermore, you can represent that characterization as a subset in the state space of the system. Okay, so this red ellipse, which I've called G at time 0, that's a set of unsafe states, just as an example now, unsafe condition. So you don't want the state of the system to enter that region. A backwards reachable set of that set G of 0, which we've labeled here in the kind of lighter red or pink, which we call G of t, is characterized as the set of all states for which, for all possible control actions U, there's a disturbance action which, under the dynamics of the system, could cause the state trajectory to enter G of 0 in at most t seconds, t time units. All right, so that's our definition of a backwards reachable set. We allow for control inputs, we allow for disturbances, so typically effects on the dynamics that we can't characterize. However, we assume that we know or we can characterize bounds on the disturbance. Using this framework, we pose reachability as a game between disturbance and control. So the control is attempting to keep the system safe. The disturbance is attempting to do the opposite because we can't characterize it. We don't know what it's going to do. And then we use that characterization to try to compute in this case, the unsafe set, so the smallest unsafe set, the least conservative set. So use the control to do its best possible action to try to minimize the size of that backwards reachable set. Okay, and the characterize, well, that's a definition of the set, but we can mathematically characterize that set too. And this is kind of where our research in reachability started, was really trying to characterize that set for continuous control systems. And this was, we did this more than 20 years ago now, working with Shankar and John Ligaros. Dimitri Bertsekas has had worked on a control characterization for reachability for discrete systems, discrete time systems. And then Ian Mitchell, who was my first PhD student, who's now a professor in computer science at UBC in Vancouver, he developed a computational characterization of this. So the theorem is that reachable set G of t is the sub-level sets of a function j, a value function j, which solves this partial differential equation. Right, so this is known as a Hamilton-Jacobi, typically Hamilton-Jacobi-Isaacs partial differential equation because of the game theory. Isaacs was a game theorist. And then on the right-hand side, there's a min with 0, which ensures that once the state trajectory has entered that unsafe region, We don't want it, the trajectory then to leave and then that trajectory to be characterized as safe. So that min with 0, freezes the trajectories at their, or so-called freezes the trajectories at their lowest value. So you characterize them as unsafe if they go through that region. And then we compute this set. We basically compute it iteratively, starting on the boundary of the set and working backwards. So if we take a kind of side view, and again, this is stylistic, but a side view of that set, what we're doing is we're propagating the function whose 0 level set is the reachable set over time. So this j of xt is the value function that we're propagating over time. And you can see if we take kind of a sideways look, we have some initial value of j of t, which looks probably some, that's some function. So we assume that we can represent unsafe conditions as some subset of the system state space. And then we construct a function, j of x at time 0, which is whose 0 level set is g of 0. And then that's the function that we propagate over time. So where we initialize it, and then over time that function evolves, and we're always capturing the 0 level set of that function, or the sub-0 level sets of that function. Okay, and a word about invariance. So we compute, as I showed before, typically we're computing that set back for some finite horizon t. And so that gives us a characterization of where trajectories in the state space whether they'll end up in that set or not in at most t time units. So, you can then partition the state space, right? You turn that state space into essentially 3 regions. The first region is the set that is either unsafe or could become unsafe in t time units. The second region is everything that's safe in t time units, if you trust the models that you're using. And then the boundary is kind of the boundary in between those sets. And that's, where you might, if the system is evolving and it's moving towards the boundary, that's where you would apply a control action, which is also computed as part of this Hamilton-Jacobi formulation to keep the system safe. Now, if that set is controlled invariant, meaning sort of more intuitively that if that set, if there's some finite time for which that set stops growing and it stays, so it doesn't change anymore, so it's controlled invariant for all t, then any super 0 level set of that set is also invariant. And that's important as we're thinking about 2 things. The first is computational over approximations of the set. But here I'm talking about a super 0 level set. So not the 0 level set, but maybe the 1 or the 2 or the 3 level set. And we can also use that for safety. Okay, so we'll come back to that a bit later when we talk about integrating machine learning into these techniques. And then finally, another thing to note is that the more you know about the disturbance action, so the smaller the bounds on the disturbance, the smaller that unsafe set becomes. The more, the more you approach the optimal reachable set. Often, the dynamics of the system are there. So even if you could characterize the disturbance set perfectly, so you didn't have a disturbance anymore, there would still be some finite volume in that set outside g of 0 just from the dynamics. Okay, so as I said, Ian Mitchell his PhD thesis was in formally proving that theorem about reachability using the Hamilton-Jacobi-Isaacs PDE. And then developing a computational toolbox called the level set toolbox for computing these reachable sets. So what's a level set function? It's really just a value function where you're looking at the 0 level sets of that function. And when we started working on this, there'd been a wealth of tools developed in the level set community, pioneered by Stan Osher at UCLA, Jamie Sethian at Berkeley, and John Cisiklis at MIT. To compute these level set functions for problems like propagation of one fluid through another, or semiconductor physics, where you're depositing one material on another and you're basically trying to track boundaries. Okay, so we applied this methodology and this sort of computational framework to this control problem. And so some of the benefits of using this are you can compute, this this set for non-convex, funky-looking sets like the one we have here. The boundary of the region is defined implicitly by the zero-level set. The magnitude of the function is the distance from, well, okay, it depends what you use. Typically, we're using a sign distance function for our representation of g of 0. And so j of xt, as we propagate it, maintains this measure as the distance from x to the boundary at any time t. And then the way we've characterized it, j is negative inside and positive outside, or you could do it the other way around, it doesn't matter. But there's one, the sign of j represents, you know, whether you're inside or outside the set. And here are some references. So the original level set toolkit is on Ian's website. You can download it, you can try it out. We've been working over the past several years at developing add-ons. So developing a framework that allows you to easily use it for higher dimensional systems, to do approximations. I'll say a few words about that. But our latest instantiation of this is given in our GitHub, and we call it Beacles. Beacles is it's a toolbox which is now implemented. You can do this computation in parallel. And so it's a sort of parallel processing implementation of the Hamilton-Jacobi. Great. So here's an old example. This is 4 quadrotors, and this was back when I was at Stanford. So those of you who've been to Stanford, you might recognize this Rotary field. And you can actually see these are old quadrotors, right? Now you've seen much more high-tech quadrotors. We actually built these. This was back in the days before you could actually buy quadrotors. And we have students flying them around. They're, each one is being joysticked by a student, but the vehicles have the control technology on board. So if we look on the right here, when one vehicle comes within a collision zone, the backwards reachable set for collision with another vehicle, then the automatic control law on board the vehicle takes over and guides the vehicles away from each other. Okay, so the students are trying to push those vehicles together, and when they get within the reachable set boundary, the optimal control takes over and guides the vehicles away. So you see around each, if you look on the plot on the right, each vehicle has 3 sets around it. That's its collision, that's its backwards reachable set for collision avoidance with respect to each of the other 3 vehicles. Okay, and then maybe one last slide before pausing for questions. You can turn this around and also compute the backwards reachable set from desired states. So here, suppose you'd like the system to get to some desired region despite the worst case disturbance. And so here, the PDE is the same, except the min and the max are switched. So now the control is trying to minimize that inner product between the gradient of the value function and the dynamics. Whereas the disturbance, again, we don't know what it's going to do, but we have bounds on it. We're assuming that that's trying to do its best to keep the system away from the desired set, so maximize that inner product. Okay, so if this is a good time to pause for questions, I see there's some questions in the chat. No, these are just, okay. Yeah.
If you have a question, you can unmute yourself and directly ask Clary. Before that, actually, I have a question, Clary. Yeah. So sometimes the minimax is over conservative. Is there like another notion like a mean expectation, like a reachable set instead of this min max?
Yes, so that's a good question. So what I presented here is a kind of a robust version of this, or like a worst best case through min max. What we're doing is we're using the min max to compute this set of states. So it's not actually, you know, if you were, for example, away from the boundary of the set. So in this case, you're trying to reach a desired set. So the backwards reachable set is kind of where you want to be. If you were away from the boundary, you don't have to apply that min over u. You can just use whatever control law you like. The idea is that when you approach the boundary, you're at the, can you see my pointer?
Yes, yes.
Yeah, okay. So when you approach the boundary, you're at that risk of becoming unsafe. So going into states where, you may be pushed away and never get to the desired condition. So that's when you must apply the min over u. So that's the sense in which we design this, like a least restrictive control that gives you a filter on another performance-based control you might be using. Now, Guanya, your question was, could I come up with some expected value or some probabilistic version? And the answer is yes. There has been quite a bit of work developing the concept of stochastic reachable sets. And this is, and there are a variety of formulations. Alessandro Abate and John Ligros, Maria Prandini, and a number of others have developed this concept for, instead of value function, expected value. Some work that we've been doing with Margaret Chapman is using a CVAR representation of the values, so a conditional value at risk. Which is which allows a certain kind of representation of uncertainty or risk averseness in the computation of the reachable set. So yes, there are different formulations, and in this talk I'm going to focus on this robust version, so the minimax.
Thanks. We got an interesting technical question from YouTube. Actually, do we have any assumptions on F in this theorem, like a controllability, I guess? He's asking.
Okay, so we don't necessarily need F to be controllable. We're assuming throughout that it's well behaved in the standard way, namely that F is assumed to be Lipschitz in X. And we're going to assume that how the control acts, and the disturbance we're just assuming lies between bounds. But when we compute a control from this and use it, we're assuming that the control is a piecewise continuous function of time. Now, the controllability issue is an interesting question. So because we're computing the least restrictive control, we're not actually needing to assume that the system is controllable. However, if we are going to be using the min over u, say, we just had that discussion of, what control to apply at the boundary, then basically we're assuming that min over u exists and that we can compute it. And that's related to the controllability of F. So to be able, maybe the broader assumption is that we assume that when we need to use it, like on the boundary, that min over u of this max of the inner product exists.
Thanks.
Okay, so let's go on.
Can I have a question?
Yeah, sure, Raphael. Yeah.
Yeah, just I saw some works where they try to model like as a Gaussian process, and there is also this reachable set, and so
yeah, and
what's the similarities? I mean, like I see that you are working with minimax, and then there is this way that you go with Gaussian process. What would be the similarity?
Yeah, and I'm going to come to that. We, as we started to integrate, so the question arises, I mean, okay, what are we assuming here? The biggest thing we're assuming, and this is this, how does this relate to the real world, is that we have a model of the system, right? We have this F function. We may have disturbances, but they act in this way, that are kind of encased within F. One of the first steps that we took, which I'll come to, in integrating learning into this methodology, is by assuming that though we don't know D, we can learn more about D over the course, the disturbance and its bounds over the course of over the course of time. That could just be continually running. And so one of the first things we did was to model D as a Gaussian process and use the data collected online to update the function D. So in the In the framework that I'm presenting now, D is simply a disturbance lying, and it's a bounded disturbance. We're going to move on to talk about Gaussian processes in a few minutes.
Okay, thank you.
You're welcome. All right, so let's move on. If I can move on. Okay, and you can combine these operators. We talked about reaching a desired set, so say a target set that I've shown here in as this blue rectangle. Avoiding an unsafe set, so think about combining those two. So you want to compute sets that reach a target while avoiding an unsafe set. We call that a reach avoid operator. And moreover, if you have a hybrid system, you could sequence these computations together. So suppose you start in one mode and you want to get to a target set in another mode. You could compute the backwards reachable set from the target set, and then ask, is there some subset of that backwards reachable set which I can define as a target set from a previous mode that I'm in? So for example, if you've got a robotic manipulation system and you're trying to do a task which involves free motion and then maybe contact, and you'd like to model both of those, so you have a free mode and a contact mode, and you'd like to switch between those, how might you characterize a task in terms of reaching a desired goal while being able to switch back and forth between those, all the while avoiding unsafe regions? Maybe you don't want that arm to move over a laptop, for example. You've got some region of the state space which you want to remain outside of. So this Hamilton-Jacobi framework is actually quite flexible in computing reach avoid operators over mode switching. And so this is some of the earlier work that we did with Ian, was to try to characterize these. Basically, when you're trying to compute a reach avoid operator, what you're doing is computing the backwards reachable set of a desired condition while masking out from that computation an undesired region and its backwards reachable set. So you can put constraints called variational inequalities on your value function so that you compute the set you want, subject to remaining outside of the value function representing the avoid set. Okay, so there's so the details of this, I mean, we've worked this out for certain examples. I would say it's not an algorithm yet because there are, there's lots of assumptions that have to be made. How do you define this, precursor operator? How do you define the intermediate target set? That right now it's very problem dependent, but the framework is general enough to allow this. Okay, but the biggest deal with these, and I mentioned this earlier, is dealing with the curse of dimensionality. And there's a community of people working in this area of reachability, coming from both the control systems, traditionally coming from both the control system side, as well as from the computer aided verification side. So people that work on model checking. This is, what we've just described is a model checking procedure. You have a model, you have a specification. In our case, we talked about the safety specification, and you'd like to ask, under what conditions does the model satisfy this specification? Okay, so there's different classes of approximations that people have developed to try to make this computation more feasible. In our case, we're solving a Hamilton-Jacobi equation. Typically, we're solving that numerically over the state space of the system. And the hard part here is the dimension of the continuous state. So for each, we're solving it numerically. So basically the methodologies require gridding up the state space. And you solve that PDE. So you basically compute those operators dj dt and dj dx, and you solve it at each grid point. So the more dimensions you have, you keep adding on more and more grid points. So the computation, it's a typical, it's a dynamic programming algorithm. So the computation is exponential. The basic Hamilton-Jacobi computation is exponential in the dimension of the continuous state. What can we do? Well, we can impose practical constraints in those vehicle problems that we talked about. Put roadways in, put protocols in. So, as you increase, for example, the number of vehicles, and you're thinking about, collision avoidance with other vehicles that you have models for, you can reduce the number of interactions, and that reduces the dimensionality of the problem. You can form approximations. And there have been a variety of different methods for both approximating the dynamics, if you approximate them with linear systems, for example, and your costs are quadratic. That's a nice calculation. So suppose you had a linear dynamics with quadratic cost, that Hamilton-Jacobi formulation can be solved using a linear quadratic regulator formulation. And we know the solution, that we have closed form solutions for that. And so people have done that for things like, linear approximations of the dynamics, or piecewise linear, or multi-affine systems. Let's look. So I've just listed a few here. The mathematical structure. So there's quite a bit of work that's been done, for example, in monotone systems. You know that your dynamics are monotone, you can reduce the computational load by using the monotonicity assumption to say something about the behavior of those reachable sets. Domitilla Del Vecchio, an alumna of Caltech, has done a lot of important work there, as well as others. Decomposition. So that's something we've worked on quite a bit. How do you take, high dimensional dynamical system and decompose it, project it down into subsets of the states, do the computation in those subsets, because that reduces the exponential, you've still got an exponentially, you've still got computation, which is exponential in the dimension of the state space, but if your dimension is lower in these subregions, then the computations can go faster. So we do those in parallel, and then we back project it to an over approximation of the state of the set. And that works if you've got an unsafe set, because an over approximation of an unsafe set can still be used to certify safety. Exploiting offline computation. Let me say a few words about the last two, actually, because that's work that we've been doing recently. So one technique that we've been using is saying, well, can we do some of the computation of reachability offline so that we can then use it, store it, and use it online? And this is work largely led by Mo Chen, he graduated a few years ago. He's now a professor at Simon Fraser in Vancouver, and Sylvia Herbert, who just graduated. She just finished her PhD this year, and she just started as an assistant professor at UC San Diego. And so they said, well, can we use this reachable set methodology to, in real time, while you're planning for robot motion planning or vehicle motion planning, like we were talking about. In control systems, we like dynamic models of systems, like our old quadrotor here. So we typically use a dynamic model, and if we wanted to plan while avoiding these constraints here, that would be quite slow, right? We get a slow but accurate plan based on the dynamic model of the system. In contrast, on the right-hand side here, robot motion planning, one of the most popular methods in robot motion planning is this rapidly evolving random trees, RRT. So it's really a sampling-based method. You find points, you sample points, and then you basically use a very simple point mass model to assume that you connect those points, and you form a plan which is very rough, but is nominally conflict-free. Yet when you try to track that plan, with your actual dynamics model, you can run into problems. So we were kind of inspired by both of these, well, reachability in the dynamic case, and these fast path planners. And we asked, could we use reachability to pre-compute a maximum tracking error bound between the high dimensional model, say the 10-dimensional model of that quadrotor, and the 2D model, which is just our method used for RRT. So pre-compute a tracking error bound, which says that the tracking, the high dimensional model can always remain within this ellipse, or this region, this bound of the planning model, and then carry that around with us. Then just use fast planning with that tracking error bound. It's like bloating either the point mass or bloating the obstacles, but bloating them in a principled way. It tells you how much you should bloat these so that you can plan using a fast robotic technique, but guarantee that your constraints. Okay, and that's a reachability problem. I can go over this quite quickly. It's the details are less interesting than I think the concept, but it's a game. You pose a game between a planning model and a tracking model, and then you can compute things like, let me just, for this animation here, suppose we're using a signed distance function. So the value function here is, this is what we initialize it with. And then each of these level curves represents kind of targets. So for example, this is a 0.5 meter target between the tracking model and the planning model, 0.75 meters, 1 meter. And when we do the reachable set computation, we're asking, what is the backwards reachable set here is the largest controlled invariant set within that target region, such that the tracking model can stay within that pre-specified distance of the planning model. And for this model that we use here, you can't do it for 0.5 meters. There's no controlled invariant set within that. There's no control that is guaranteed to keep the tracking model within 0.5 meters of the planning model. But for 0.75 and 1 meter, there is some volume in there. And that reachability computation gives us that volume as well as the control law to use as the tracking model gets close to the boundary. It pushes it back in this region to guarantee you have a 0.75 meter distance, a guaranteed distance between tracking and planning model. And so these are the sets. So this is an example where we had a 3D model tracking a 2D point source, so we could visualize it. These reachable sets. If once you can see, this is a 3D kind of Dubin's car model. So you see that, that ability to turn to the left to stay within, or to turn to the right to stay within that set. And we can use it. Okay, so let's just look at this simulated example. Here's a tracking model, which is a 10-dimensional quadrotor, and it's tracking a 3D point source to get from the left of the screen, or the left of this sort of box, over to a goal on the right-hand side. And it discovers, in a simulated sense, these obstacles as it's moving. So what we've plotted here is the projection of a 10-dimensional tracking error bound into the 3 dimensions of X, Y, and Z. And then we're following that using this is actually using RRT. So we pre-computed that 10-dimensional set. We're displaying its 3-dimensional projection as we use an RRT method to try to get over to the goal on the right-hand side. And as long as the vehicle sensors can detect those obstacles before this tracking error bound hits those obstacles, then basically the guarantees of RRT, whether there exists a path or not, hold. Okay, so we developed this. We developed this a couple of years ago, compared it to doing what is sort of traditionally done before, which is just planning a path through RRT and tracking it using an LQR controller, for example. And you can see then you don't get like guarantees that the tracking model, these little axes represent the tracking model and the planning model. Here, the tracking model is outside the tracking error bound. But using this reachability-based method, which we've called FasTrack, for fast and safe tracking, you get that kind of guarantee. And you can do some neat things with this. So we were flying our little quadrotors around the lab. This was a couple of years ago, so we were in the lab flying quadrotors. And you can try to switch. You can think about applying this to a couple of different planning models. Maybe a very low dimensional planning model that you could plan with very quickly, maybe a little bit higher dimensional planning model that you could plan with more slowly, and then, a tracking model, which is your high 10-dimensional model or whatever. And if you compute these tracking error bounds for these, different planners, intuitively, the fast planners, so the very low dimensional models, have bigger tracking error bounds. The slower planners, maybe a little higher dimensional, are going to have smaller tracking error bounds with the tracking model. And so using reachability, you can switch between those. You can figure out, I have to go through that narrow corridor. It's smaller than my tracking error bound. Why don't I switch to a slower planning algorithm? And you can kind of schedule these. So this is what we call meta planning. So we did this in collaboration with Alan Yang, who works in Shankar Sastri's group and one of the kind of lab setups they're building is an ARV, augmented reality, virtual reality system, where Jesse here is path planning. Let's just play this quickly. Jesse is giving some waypoints in the virtual reality system to this planner. So this is for a quad rotor that's meant to be flying through some hoops in the lab. So he's just creating, he's not doing RRT, he's just creating a path by giving it waypoints. And then the quad rotor is going to be using FasTrack to track that path. So he inputs that, and then it's passed over to the real system. And you see both in the AR, VR that Jesse's looking at, as well as the real system, this quad rotor following that path. It deviates from the path, but it deviates within the tracking error bound at each point. We've also used FasTrack to do other real-time planning.
Hey, Clary, sorry, would you like to take two questions?
Yeah,
because we have two questions regarding. Okay, because we have two questions regarding the RTA plus like planning. So
yes.
One question from Isung from Caltech, is this path planning like just waypoints, like I guess kinematics planning, or motion planning, including some dynamics?
That's a good question. So the RRT, it depends. You could do, it depends what you use as your base planner. So FasTrack is kind of a wrapper around, it can be used with a variety of different planners. So we've used it with RRT, which is just a, RRT is really just, it gives you sample points, and then it assumes that you can fly using that point mass model between those sample points. And so there, but FasTrack uses like a motion model of the vehicle. In that example that I showed in simulation, where we were using a 3D RRT, the actual tracking model was a 10-dimensional quad rotor. So we're doing full motion planning there. But the motion planning is coming from the combination of the RRT and then the safe controller that keeps the tracking model within that tracking error bound of the RRT plan. We've also used it with other planners. So with a higher dimensional model, we've used a model predictive control as a low dimensional but higher than 2D planner. So we've used it in a combination of planners.
Yeah, I guess there's a trade-off like between the fastness and the size of the bound.
Exactly. So as you get as you increase the complexity of your planners, then the planning slows down. But sometimes you have to do that to be able to get, if you're planning through narrow corridors in that example that I was using, then typically you want to use a slower planner.
I see. We get another question from Zexiang. Are the control used to bound the tracking error and the control used to tracking the nominal path decoupled somehow?
Yes. So there's the control law. Okay, so to get into a little more detail, we assume that there are shared, there's some like shared state variables between the planning model and the tracking model. So the tracking, so so for example, in the point mass model, we're coming up with, desired velocities for the vehicle to track the plan. And that's kind of the performance model. That's the model you're using to track the plan. But when the vehicle comes to the boundary of this, if the tracking model gets to the boundary of the tracking error bound, then the safe controller takes over to push it back in. And maybe you saw a little bit in that virtual reality experiment that the vehicle was a little bit jumpy. it would kind of track for a little bit, and then it would get to the edge, and there would be kind of a pushback. So one of the things that we haven't done very well in general with reachability is blend the safe control with the performance-based control. But FasTrack is using both, a performance-based control to track the plan and a safe control to apply that comes out of the reachable computation, the reachable set computation, that gets the vehicle back to its path if it veers close to the tracking error bound.
Thanks.
Yeah. One more example before we move. Well, let's actually, okay, I'm going to go through this. Actually, I'm just going to say a few high-level words about this example class, because I think it's important and it moves us towards the learning work. And I see that we're coming up close to we want to end about 10 minutes early. So one of the ways that we've been using FasTrack and reachability in recent work has been to try to plan paths for robots around people. And here, you know, people are obstacles, but they're kind of crazy and intelligent obstacles. And we want to be able to use predictions of how people are going to move so that we can plan robot motion, like this quad rotor moving around a room where a person is moving. So we can do that intelligently. And one of the model classes we've spent a lot of time with, this is a model class of a person, or a predictive motion of a person, are Boltzmann models. This is actually a Boltzmann model from physics. Beta here, if I can get my pointer back, beta is this inverse temperature parameter, and this Q represents a value function, which is kind of a measure of the efficiency of this model. So what does it say? The probability of the human actions, how the human is going to move, is more efficient according to the goals of the human. So this function Q encodes both the state of the human, the action of the human, as well as goals. So what are the possible goals that the human could be moving to? So in this example that I've stylized here, the goal is the door, right? The human's trying to move towards the door. At least that's what the robot thinks. And so the model of the robot has of the person says that, you know, the actions that the person takes that move it, like that are more efficient towards its goal, for example, moving in a straight line path towards its goal, those actions are going to be more likely under this Boltzmann model. And beta here is a parameter. It's a single parameter, and it's kind of a measure of the spread of the distribution. So as the model becomes more certain, beta becomes, so, you know, beta can change. And, you know, as the model becomes less certain, the spread of how this person moves can spread out in this model. So for example, if the person suddenly turns around because they've forgotten their keys, the robot would look at that and say, well, they're not moving in a direction that is efficient towards their goal. So we're going to update beta. And this is sort of an integrating a little bit of, not really learning, it's just a Bayesian update on beta to say, I want to update beta to indicate that this model may be wrong, or it may, you know, it's not modeling a kind of rational choice according to the goals that we've enunciated for this person. Now, this Boltzmann model is a fairly standard model used in the robotics community for predicting human motion. This is a work that we did in collaboration with folks in Anka Dragan's group, but we introduced this Bayesian update on this parameter beta, and we asked if we could use this now for robot motion planning. So here's sort of that scenario set up. Sylvia here is our test human, and she's walking across the lab to the door, which is over here on the bottom left-hand side. And a quad rotor is trying to plan a path across the lab. Let's play it. This is so Sylvia's moving across the lab. You can only hear my voice, right, and not Sylvia's. Yeah. Okay. So Sylvia's moving in a way that that the robot first may think is irrational. She's trying to avoid this this region on the floor, which is kind of simulating a coffee spill. So she's not taking a straight line path. And thus, as the robot is moving, let's just play that one more time so you can see the spread of the distribution coming out of Sylvia. Okay, so these kind of colored blocks coming out of Sylvia represent the prediction, so the probability of Sylvia being at those points in the next couple of seconds. And on the right-hand side, you can see kind of a top-down view. As she starts to move around, that distribution spreads out because the update on beta, that basically since she's not moving in a straight line path, which is efficient towards the goal, which is the door, her the spread of that distribution becomes large and the robot has to plan around her. Okay, and we've done this with you know, scaled this up to multiple people and multiple robots. I think I'll skip that just to end the talk. I'm going to skip a little bit here. Say one word about computation. One of the most recent works that we've done with Samuel Bansal is to say, let's actually, instead of using the kind of standard level set methods for computing these Hamilton-Jacobi functions, which require a gridding up the state space, let's try training a neural network to be able to compute the solution to this Hamilton-Jacobi equation. And this was enabled by, earlier in the summer, there was a new paper, a new project release called SIREN, which stands for Sinusoidal Representation Networks. So basically neural networks that are using sinusoids as activation functions instead of the standard, you know, ReLUs or other kind of, you know, piecewise linear functions that have been used in the past. And we're getting really good results with this. Just shown here are two scenarios. We did a direct computation of a 9-dimensional 3-vehicle scenario. So in the past, we haven't been able to do 9-dimensional Hamilton-Jacobi computations. In the bottom, there's a 2-vehicle scenario where each vehicle has 5 dimensions. So it's a 10-dimensional computation. These always required us to do, you know, protocols or decompositions in the past. Now we can solve those directly using this, Samuel trained a SIREN network to solve the Hamilton-Jacobi equation. And we've just submitted this. So we're asking now how we might use this for other higher dimensional systems, like, for example, walking robots. With Kaushal Srinath, we're working on, you know, high dimensional models. He has these beautiful walking robot models, as well as a Cassie walker in his lab that we'd love to work with him on. Okay, let me end the talk now by just with one last point to say, as we're learning these sets, so let me just walk you through this last animation. I'll show you some results. You know, we talked in the very beginning of the talk about reachability, and, you know, as you learn more about the disturbance, you could actually move from, say, a less conservative, or sorry, a more conservative unsafe set to a less conservative set. But also you can use super zero level sets to certify safety. So we started developing, and we've been using this more recently now in our work with where we integrate machine learning into reachable set computations by initializing the reachable set computation on the smallest candidate set such that the disturbance model is validated. So what does that mean? As the system, so you start out with a model of the system, you start out with some bounds on the disturbance, and then you start running the system and it starts collecting data about the disturbance. And as long as that disturbance model is validated, like as the system moves around the state space, then you basically keep the model that you started with. But what might happen is that, you know, you're flying along, for example, and you get to a point where you see that the disturbance is larger than you had predicted at that point. Namely, you know, if you stayed there, the disturbance might push you into the unsafe region where you hadn't expected that. So we use these super low zero level sets. What we do is we expand immediately. This can be done in real time, right? You've already computed the level set function. Expand to a super zero level set, which still allows the certification of safety under the new disturbance model. And so this is a Bayesian structure that we maintain to be able to figure out what is the smallest candidate level set. So the value of V such that the disturbance that we're measuring is inside the new disturbance set. And then over time, we continue to collect data. And, you know, over time, if you're getting more and more disturbances that show maybe that was an anomaly, hopefully you can, you know, shrink the disturbance set. So you've got some kind of, you know, for the data that you're collecting, this is a reasonable. And we've flown that now. This was a few years ago in work that we did with Jaime Fizak and Kene Akamatalu. We flew that with our quad rotor in the lab. This is a two-dimensional model, so low-dimensional model, proof of concept, where the vehicle is trying to fly step trajectories up and down. So it's trying to stay within a safe envelope, pre-computed using a model, but it's got a large disturbance that is just turned on in the midst of the experiment. And we flew two experiments and we superimposed them on each other. So in this ghosted out experiment, the full reachable set is still used, whereas in the non-ghosted out quad rotor represents that online model, disturbance model update. And here this was a question earlier, here we're using a Gaussian process representation of that disturbance. Okay, and then in the recent work that Sylvia and Jason and others have worked on, so Jason's a PhD student who's jointly supervised with Kaushal Srinath and me. We applied this using our now, the new methodologies we've been computing for computing these reachable sets in real time to a 10-dimensional quad rotor. So previous video was 2-dimensional. Now we're asking the quad rotor, a 10-dimensional near hover model, to fly these figure eights where we suddenly introduce wind and we ask, you know, this emergency contraction of the set. And we've just submitted this aircraft. Okay, I think in the interest of time, I'm not going to get to the kind of very last point that I wanted to get, which is how might we integrate perception-based control into this reachable set framework. So here, you know, we've got a set of experiments where we've got a camera on board a robot. The vehicle knows where it is. It has some goal over here around the corner in the lab, but it doesn't know what's in between. It has to figure out, you know, what obstacles are in between and maneuver around that. And we asked if we could train a neural net for perception using optimal control and then integrate that control scheme into a safe learning framework using reachability. And that's really, you know, one of the projects that we're pushing on now is using reachability as a kind of, a kind of maybe a bookkeeping method or a safety envelope around different learning schemes. So with that, because we're running out of time, I'd like to skip to the end so I can acknowledge a lot of the folks who have worked on this with me. Namely many former students. So former students who graduated and are at different places, students who are now in the group who've been working a lot on this are Andrea, Jason, Forrest, Dongun, Vicens, and Varun. But this is the work of many former students who are, you know, often there. Even, you know, from early work of Ian we presented, but many recent students. For example, you know, Jaime, who's now an assistant professor at Princeton, Kene, who's now working at Uber, et cetera. And I'd like to acknowledge also a lot of the funding agencies who funded this work. And thanks very much. Maybe there's a minute or two for some more questions.
Yeah, thanks for this great and very exciting talk, Clary. If you have any question, I guess you can directly unmute yourself and interact with Clary. Let me check if we have a question from YouTube.
Yeah, I can see questions on the Zoom chat, but I'm not running YouTube here because there's a delay. And
yeah.
Hi,
Before
Claire.
that, sorry. Yeah, go ahead.
Sorry, can I ask a question? Oh,
sure.
Hi,
Go ahead.
Yeah. So it's a very interesting talk. I have a question on the first part, the reachability set.
Yes.
So I wonder, do you need the information for the complete dynamical system, that nonlinear f of x u dt, that complete function, to compute a like the local reachable, backward reachable set? Because Yeah, because I would imagine that sometimes we know what the dynamical system is very well for the region we are in, but we may have not that much information about the system like outside.
Yeah. Yeah, so that's a good question. So in the work that I just ended on, the thing we don't know, and I think this is quite typical, is we don't know the environment. We may have some representation of the environment, but we don't know what's going to be there. You know, you don't know the obstacles that are going to come up or what's going to happen. And typically, you know, in control systems, we do have a fairly good model of our like ecosystem, and maybe even other like vehicles around us. We just don't know what they're going to do. So that's been our assumption in that last set of work, that we would like to be able to use reachability. We'd like to be able to use models that we have sensibly, but we'd like to be able to integrate learning for these challenging problems like perception of the environment around us, but then still be able to use reachability in a way that allows us to make some, I hesitate to say proofs of safety, because when you start allowing the environment to do anything, then we don't have proofs anymore. We don't have models, so we can't prove anything within the models that we have. But what we can do, and this is what we're pushing on in that work, is this idea of introspecting on the environment. So we can compute you know, that the system will remain safe as long as we make these assumptions on the environment. And then we kind of impose, or we ask, okay, environment, you have to satisfy these assumptions, and then we can make some guarantees.
Yeah,
so, so that's really the split there. And so we typically assume for the reachable sets that we know the model of ourselves, and maybe we have some knowledge of the dynamics of other things, but we don't know what their actions are going to be.
Thank you very much.
You're welcome.
Let's have the last question from Matthew. Matthew, could you?
Yes. Hi. Hi, Claire. Good to see you again. I have just a quick question. I know this is more of a broad overview. You kind of talked about some new work maybe in some of the learning with reachability. I was just kind of wondering. I know that with respect to a lot of the Hamilton-Jacobi PDE, you know, that's essentially, for lack of a better word, an exact solution provided you know F. And I know you've done a lot of work with if you don't know disturbance properly. But with some of this learning and machine learning, you know, especially with respect to collision avoidance, you know, what does that really mean as far as guarantees when you kind of approximate these situations? Because you could have a corner of the state space that maybe you didn't have a lot of data, and then you run this on a system, and then it goes kind of squirrely, as we've seen a lot of machine learning. And obviously, with respect to something like facial recognition, if Facebook, you know, incorrectly categorizes somebody's face 10% of the time, that doesn't really mean anything. But if you have a, you know, automobile system, that could be catastrophic. So I'm wondering how that all works.
Yeah, so I agree with you, Matthew. I mean, we're coming from the same place here, and this is new work. That we're doing with this Siren network to compute solutions to Hamilton-Jacobi equation. So I'm just going to say maybe 2 points about this. The first is that the computation, the network-based solution of the Hamilton-Jacobi equation is a grid-free solution. So we've been searching for years, and I know you guys are interested in this too, about like, how do you really try to resolve this exponential dependency of computation on the grid? And so, and nothing that, well, okay, there's been different avenues that we've tried, but here, the excitement is that this network is basically a grid-free solution. Now, you're right, the less data you have in certain regions of the state space, the less accurate that solution is going to be. So that's where we're putting in the work now, is trying to understand how accurate that solution is when we compare it with, you know, other methods that exist to compute these high dimensional solutions. And the exciting thing is, for those solutions that I showed, you know, we haven't been able to compute 9 or 10D solutions using level set methods directly. So we've done some approximations like decompositions. The hop-flax methods that you've been working on are really exciting, and that's something that we've been also excited about and working a bit on. But the solutions that we've been computing via Siren are computing solutions that are more accurate than the level set methods, even for low dimensional examples. Now, I'm saying that this is all empirical now because we can't prove anything, but we can test these out and compare them with level set solutions on low dimensional examples. And that is, I think what's happening is that in general, the neural nets are, because we're constraining, there's a method where we train it to learn the initial data, and then we train it on time horizons sort of iteratively for computing these solutions to the PDE. And the solutions are, the neural net is figuring out, what points to do the computation on so that it matches, so that it minimizes this loss function, which is the deviation with the true solution. And you can put in the equation as constraints. So I think it's a really exciting avenue to take, but I agree with you. What can we say about proofs? I mean, when it comes to that, what can we say about proofs of level set methods? Because they're an approximation, right? They're a grid.
Yeah, there are an approximation. I guess somewhat your answer is that the learning is based around the Hamilton-Jacobi. So you can kind of say that the Hamilton-Jacobi structure still exists. It's merely
totally. That's really important.
So you're trying to approximate just that HJ be a solution,
yeah,
and
you give it. So you're telling it, here, neural net, learn a solution to this Hamilton-Jacobi equation with these constraints and this initial data. And so what we've, this paper of Siren came out in June, and it was, Samuel found it, and he is sort of in the computer vision community. And from June to like last month, we submitted it. That was the focus of the work, was trying to understand how to train the neural net to be able to solve the Hamilton-Jacobi equation.
Okay.
Yeah, we can talk more about that. I think there's lots to learn here, and we were sort of just starting.
Yeah, I know. I mean, normally I would say, well, it's right around the corner for BRC, but I don't know if that's happening. So
yeah.
I can email, and we can set up a chat sometime.
That would be great, Matthew. Yeah, look forward to that.
Okay, thanks everyone, and thank you again, Clary, for this great talk. Thanks, happy Thanksgiving, everyone. And the next week we're gonna have Professor Jean-Jacques Slotin from MIT talk about contraction analysis in learning, control, and optimization. Hope to see everyone the next week. See you.
Thank you very much, Guanya. Thanks, everybody. Have a very nice holiday.
You too, Clary. Thanks.
All right, bye.